We complete our treatment of the H2O MO diagram in this clip. In the last clip, we took the first order H2O orbitals, mixed them to make them the second order MOs. But remember that it is traditional in an MO diagram to put on the left side the initial atomic orbitals, which I'm now redrawing from beginning. The three initial atomic orbitals on the oxygen P at minus 15 EVs, and then at minus 32 EVs, the oxygen S orbital. On the way right side, we put the peripheral orbitals where molecular geometry equivalent orbitals have been added and subtracted, minus 14 EVs. And then it's only in the middle panel that we keep the same orbitals. So this orbital is unchanged in energy. That's this one here. This one has gone down in energy. And similarly, this one has gone up in energy. It's actually not clear which one is the highest energy orbital. So I'll put it in this diagram, the highest energy. I'll put this one with the highest energy, but I'm actually not sure it's the highest energy. They've gone up in energy. And then notice that this orbital here is an sp hybrid. It's at lower energy. And then at significantly lower energy will be the actual bonding orbital here. We have 8 valence electrons in H2O, 4 filled orbitals shown here, and we draw the tie lines. Is that it? I believe those are the correct. Oh, and then we have to draw the anti-bonding ones. I hate these tie lines, by the way. And that is the H2O MO diagram. Now that certainly took a lot more time to make than the Lewis structure and valence bond methods. And why did we do this? And the reason why is that the energies are exact and can be verified by experiment. Until you can verify something by experiment, in physical sciences, it's not totally there yet. And we're going to have 4 different energies. This one, I'll put them in red. We'll have this as an energy. This one as an energy. This one and this one. If I were to put that on a horizontal scale, it will look like this. I'll have low energy here. High energy here. I would have a peak at low energy. Then I would have 3 peaks at higher energy. This is what we predict the photoelectron spectrum to look like. And that is the water photoelectron spectrum. It turns out that there's you can even tell how much S character. S orbitals, central atom S orbitals show very weakly. And that's why here, this next, the first peak is relatively not very big. It's because it's mainly on S, but the 4 peaks are exactly as we expected. And notice that this is not what we would have expected from valence bond theory. In valence bond theory, remember we had the 4 orbitals. We had one bonding orbital like this, a second bonding orbital like this, and 2 lone pairs like that. And that's the same thing that we expected from the Lewis structure. 2 single bonds, 2 lone pairs. We did not expect that the 2 bonds would be at different energies, and the 2 lone pairs would be at different energies. These are the bonding orbitals. These are the non-bonding. Only MO theory has an experimentally accurate prediction of energy and is experimentally verified. And therefore, although MO theory takes a lot more time, MO theory is a lot more real. In the remaining clips of this lecture, we're going to figure out how it's possible that these 3 theories can coexist at the same time.